So yesterday, okay, we started out with all the atomic structure stuff. Okay, we talked about the 4 points of the atomic theory, right, which we said were going to be important, especially 3 and 4. Okay, because 3 and 4 talk about what happens in a chemical reaction. They also tell us that it is impossible to, in fact, turn an atom of one thing into an atom of something else. You can't change an element. Okay, you can make compounds, you can rearrange compounds, you can do all of that, but you can't change the atoms that you start with. Okay, not in a chemical reaction, at least. Okay, now if you have a particle collider or you have a nuclear power plant, then that kind of thing does happen, but that's not a chemical reaction. Okay, that's like a nuclear reaction. It's entirely different. Okay, basically what Dalton was saying is that you cannot change the fundamental particles. Okay, now, once Dalton had come up with his theory of the atom with the 4 points, then people asked him what it looked like. He told them he thought it was a sphere, and then later on, Thomson comes along, he discovers electrons. The sphere model kind of goes by the wayside because it can't explain his findings. And that's how all science works. Okay? What we know changes when it can't explain something we learn. All right? Now, this happened actually in my lifetime, which tells you how old I am, but when I first started high school, okay, all living things were grouped into only 2 groups. Things were either plants or animals, and that was it. Okay? Even though people knew that some things just didn't fit in either of those 2 groups, but rather than change their thinking, they just forced things into groups. Okay? As a prime example, fungus. Okay? Fungus is not a plant. It is also not an animal. But because it grew out of the ground, people said, yeah, it's kind of like a plant. Just put it in the plant kingdom. Doesn't matter if we're wrong. That's where it should go. That doesn't make any sense. Okay? If you're a plant, what do you have to be able to do? Photosynthesis. Fungi don't do that. Okay? A fungus actually digests food in a similar way to us. Okay? Except its digestion isn't internal, it's external. Okay? But for the longest time, people just jammed fungus into the plant kingdom because, well, it grows in the ground. Okay? Plants grow on the ground, it makes sense. We'll live with that. Okay? It wasn't until later on that people said, you know what, we just can't keep doing this. There's other things that don't fit in these 2 groups either. And in fact, it exploded and it went to 5. Okay? It went to 5 kingdoms. Right? Now there's plants, there's animals, there's fungus, there's protists, and there's the monorans. Okay? Because in the monoran group, there's all these like bacteria and things like that that are simple single-celled organisms that have different kinds of cells than we do. Okay? They don't fit in the plant or animal kingdom. Protists are all single-celled organisms, okay, that also kind of don't fit in plants or animals. This is where you'd find like amoebas and paramecia and things like that. Okay? They're not really a plant, they're not really an animal, they don't fit in either one of those kingdoms. Fungus obviously needs its own kingdom. Okay? It's a fundamentally unique type of organism. Then there's still the plants and the animals. Okay? But when things are discovered or we learn something and what we thought was right doesn't work anymore, we have to change what we think. Okay? And that's exactly what happened with the models of the atom. J.J. Thomson discovers electrons. The solid sphere model doesn't explain that. He has to make up a new model. Okay? When protons are discovered, then the plum pudding model has to go out the window. It doesn't explain that. Okay? They come up with something new. Okay? Neutrons are discovered. Well, then we got to come up with something new. And that's really where we're at right now. Okay? In terms of the notes, not where we are in real life. But okay, we're at that point where what does the atom look like? We know it's got these particles in it, but we don't know its shape. And no one really has a good explanation. Everybody's got a different idea which one's right. Rutherford's idea was that the atom has a central dense nucleus that's big. Okay, that's incredibly small. I thought it was incredibly small and incredibly dense. Sorry, I said that backwards. Okay, that's where all the protons and the neutrons are, and the electrons just kind of orbit around it. That was his idea. Okay, he did an experiment to prove this. Now, he used what would be considered now very old technology. Okay, he used a setup that had a ring of photographic film. Believe it or not, cameras used to have this stuff called film in them. You guys are from the digital camera generation. Has anyone actually seen a camera that had film in it? Okay, a few of you. Good, that's good. All right, so anyway, the film, how it works is when you expose it to light, it changes. Okay, it goes from being kind of a darkish brown color to a light color. All right, and if you're doing that properly in a camera, the image that comes through, the light that comes through forms an image of whatever was in front of the camera. Okay? If you just take the film out and do this, then all you get is bright exposed film. Okay, the longer you hold it, the more exposed it becomes. A camera's shutter speed, okay, is very fast, right? So it only exposes the film for a short period of time. Okay, what he did is he took that film and he set up an apparatus like this. He put film all around. He had a source of alpha particles, essentially kind of like an X-ray machine. Okay, and he had a piece of foil made out of gold. Okay, you would certainly not like bake a potato with this thing. Okay, very valuable gold foil, but very, very thin, only a few atoms thick. Right, so it's incredibly thin. And his idea was that if he's right, and atoms are incredibly small, all the X-rays will go right through. Okay, none of them will be stopped. They'll pass right through the film, and he'll get this bright exposed spot on the back of the film. Okay, he was wrong. A bunch of the light, the X-rays that came through, were actually scattered. And he had spots, exposed spots, actually kind of all over the place. Yes, he had quite a few in behind. Okay? A lot of the stuff did just go kind of straight through. But a lot of it was deflected. Okay? Which says that there had to be something in that gold foil that was causing those light particles to bounce off and be deflected. Okay, kind of like if you had a pool table, okay, and you had a bunch of balls on the pool table, and you pushed one ball through, right? It would hit some, and it would deflect off. Okay, that's kind of what happened here, and that was shocking to him, okay, because he honestly thought they would go right through. That atoms were that small, right? What that proved was atoms look something like this. They have a central dense nucleus, but it was bigger than he thought. Okay, surrounded by an area where you can find electrons. Some of the particles would go straight through, like these ones, completely undeterred. Right? Other ones would get close to a nucleus, hit it, and be deflected. Some would come straight back if they hit it straight on. So basically, he said after his experiment, he said, I was so shocked. It was like if I shot like an artillery shell at a piece of paper and had it bounce back. Okay? Now, he's a scientist. He exaggerates things for the purpose of demonstration, but okay, that's how he felt it was. Okay, these particles should have just all gone through, but a bunch of them deflected off, and that proved that there had to be a central dense nucleus. It proved the existence of the nucleus and the nuclear model of the atom. So Rutherford, is he kind of important? He's really important. Okay, next to Dalton, he's probably the most important guy. Okay, so Rutherford essentially proved, okay, that there was a dense central nucleus where the heavy particles were located and the electrons surrounded this nucleus. All right. Now you'd think after a groundbreaking experiment like this, things would calm down a little bit. People would go, cool, now we know what the atom looks like. Except that now they found something else to complain about. Okay, it's human nature. So they said, okay, fine. The protons and the neutrons are in the nucleus. Rutherford's good on that. His experiment's good. So what are the electrons doing? Okay, electrons are really, really small. Okay? There's no way you're going to do this experiment and find out where they are. Okay? They're too small. They're moving all the time. Okay? So there's no chance in kind of locating them in that way. So better experiments had to come along that would tell what the nucleus was doing. So Rutherford, he said, I think the atom looks like this. There's the central dense nucleus, and the electrons all orbit in these equally distant orbits that are just offset a little bit. The bigger an atom is, the more of these orbits there are, and the more crowded the electrons are going to be. Okay? Well, it was found that that couldn't explain some other things. Okay? So Rutherford's model only lasted for a little while. Not the nucleus idea, obviously that stayed around, but his idea of what happened with the electrons. Okay? So a guy named Bohr, okay, came along, and he was doing a lot of experiments with electrons and what do electrons do, where are they located, trying to figure them out. Okay? And what he found was that electrons have different energies. And they have different energies because they're attracted to the nucleus. And the closer they are to the nucleus, the less energy they have. Okay? How many of you have gone over kinetic and potential energy before? Okay, you've heard those terms? Okay? For potential energy, the further you are from the ground, the more of it you have. Well, it's kind of that way for electrons. Okay? The further away from the nucleus they are, the more energy they have, because the faster they have to move. Okay? If they're close to the nucleus, they don't have as much energy. Right? So he said, I think that electrons move in orbits around the nucleus like planets around the sun, except that there's more than one electron in each orbit. Okay, now you're probably thinking, wouldn't that be bad when they run into each other? But no, why won't the electrons run into each other? Well, not only are they moving sometimes at the same speed, not always, but they both have the same what? Right. What are they going to do? They're going to repel each other. Okay? They want to stay as far apart as possible, so there's not really any chance of electrons running into each other. Plus, they're incredibly small, okay? And the space of an atom, even though an atom is also incredibly small, is very large for something that tiny. Okay? So there's lots of room for electrons to move around within the atom. Okay. So Bohr's model is still generally accepted, but it's accepted only in this way. If you were to take a picture of an atom and freeze it in time, you would probably see something that looks like this. But the reality is that an atom is dynamic and it's always changing. Okay? So this model doesn't really explain the fact that some electrons move away from the nucleus and back to the nucleus and further away and back. Okay? We see that that occurs all the time. In fact, it's how photosynthesis works. Okay? When light strikes a leaf, okay, the electrons that are part of the chlorophyll, okay, actually become excited, they gain energy, and they move away from the nucleus. And then, when the light goes away, they fall back. And when they fall back, they lose their energy, and that energy is used to make sugar. Okay, that's the energy that powers photosynthesis. Everybody follow me there? Okay, if you have a watch that has like the little markings on it that glow for a little while after it's been in the light and you go in the dark, it glows for a little while. Okay, it's the same idea. Okay, the electrons in that material, that glow in the dark material, they gain energy, they move away, and then when that source of energy is gone and you're in the dark, the electrons begin falling back towards the nucleus and they give that energy off in the form of light. And so they glow for a short time. Okay, Bohr's model couldn't really explain that. Right, so we had to move to the last model, the one that we currently accept. Okay? And that is Louis de Broglie's electron cloud model. We also sometimes call it the quantum mechanical. Okay? His model says electrons exist in a cloud around the nucleus. There are areas within this cloud where an electron is likely to be found. Okay? But it's not in a fixed orbit like Bohr said. Okay? Where an electron is dependent on how much energy that electron has. Okay? So in reality, if you were ever asked to draw a picture of an atom, okay, it's pretty easy. Draw a nucleus and then draw a cloud, okay, around it. Okay? Now, if I was asking you to do that, I would also ask you to write in the right number of protons and neutrons and electrons. Okay? Has anyone taught you guys how to do that? How to calculate the protons and neutrons? Okay, just for a quick review here. Okay, on the periodic table, the atomic number. Okay, so for lithium, the atomic number is 3. That means it has how many protons? 3. How many electrons? 3. Okay, protons and electrons are easy. They're the same number and they're the atomic number. Okay, neutrons is different. To calculate the number of neutrons, you take the atomic mass, this number with all the decimal places in it. On the periodic table I'm going to give you, it's 2 decimal places. Okay? You take that number and you subtract the atomic number. And then you round to the nearest whole number. Okay? So if for lithium, that would be 6.94 minus 3, which gives me 3.94. Well, I can't have 0.94 neutrons. I likely have 4. Okay? Everybody follow there? All right, so if I asked you, draw an atom of lithium, okay, you would probably do something like this. I would draw a nucleus, okay, and maybe go P equals 3, N equals 4. Or I would just go 1, 2, 3, 4, 5, 6, 7, okay. Make 3 of them positive, make 3 of them neutral, okay. And for either one of them, I would draw a cloud and go 1, 2, 3. Cloud. Okay, pretty straightforward, right? Okay, the big thing there would be, do you remember what model we currently accept, and do you know how to calculate the number of particles within that particular atom? Okay, I would expect that you would probably get a question like that at some point. Okay, be it on a quiz or an exam, that's kind of the thing that would come up. Okay, questions on any of that? All right, something we didn't get a chance to talk about yesterday, and that is this idea of splitting the atom. One of Dalton's points is that atoms are indivisible, and they are indivisible by any physical or chemical means, okay? But they are divisible by nuclear means, okay? So there's two things that can happen that can change the nucleus of an atom: fission or fusion. Okay, either one of those things can change the nucleus of an atom. Okay, fission means to do what to the atom? Split it. Okay, fusion means to combine with another one, push them together. Okay, now for the most part, we use nuclear fission reactions for nuclear power. Okay, nuclear fusion's a little tougher to make happen and contain and things like that. Okay, so what we have in a nuclear power plant is essentially an emitter, okay, that shoots out particles that can break atoms, and we have fuel rods. Okay, a fuel rod is just a metal rod, and it's got embedded on its surface fuel pellets. Okay, so those pellets are made of enriched uranium. Okay, so they're concentrated uranium pellets. Okay, the particles come out of the emitter, they strike the fuel pellets, okay, the uranium starts to break, okay, and when it breaks, it releases, the uranium atoms, start to break, okay, they release a lot of heat. Okay, what's the heat used for? Boiling water. Turning water into steam, the steam turns a turbine, that generates electricity. That's how a nuclear power plant, in a simple sense, works. Okay, obviously there's far more things to it than that, but in general, that's how it works. Okay, a lot of heat is generated by this, so a lot of steam can be made, and that can turn turbines and make electricity. Okay, essentially almost all forms of electricity are generated by having a turbine of some kind. Okay, it's how do you turn the turbine? Is it wind? Is it burning coal or whatever? Okay, all right, so that one can be controlled. Okay, and we want it to be controlled, otherwise you have really serious problems. Okay, so if suddenly you don't need quite so much power, you simply pull the rod out of the path of the emitter, okay, and expose less of the fuel to the emitter, and then the reaction slows down. Okay, if you want more power, then you expose more of the rod to the emitter, and you get more fission happening. Okay, what's dangerous is if anything happens to this and it gets locked into position, okay, then it becomes overly hot, and then you have a meltdown. Okay, essentially all the water evaporates and the heat can't be contained, and the whole area melts down. Okay, and that's bad generally. Okay, all right, that's generally a controlled reaction. If you don't want a controlled reaction, we call that a bomb. Okay, building a nuclear bomb in principle is actually pretty easy. Thankfully, getting the materials is more difficult. I say easy. In principle, it's easy. It's actually, you need quite a bit of high-tech equipment. Okay, but essentially what it is, a simple nuclear device, is a bunch of high explosive, a casing made out of high explosive, TNT, C4, plastic, okay, something like that. Okay, and a big wad of plutonium in the middle. Okay, all you do is detonate the high explosive, and because you've made this casing that's shaped a certain way, all of the matter from the detonation is focused inwards, and so it hits the big lump of nuclear material in the middle and starts a chain reaction of splitting atoms that leads to kaboom. Okay, and a big mushroom cloud and the end of everything anywhere nearby. All right, everyone follow me there? Okay, so that's the idea of how, kind of, in general, how that works. Okay, I can tell you how to make a nuclear bomb in that way because I won't get in trouble. It's a lot more complex than that, but it's simply, that's kind of what it is. Question, Pete? Yep. Well, you can shut off the emitter, but the problem being the emitter is either on or off. There's not really a different amount of emitter, but if this gets going, remember that the atoms that are in here are breaking, and their pieces go off and break other atoms. That's what causes the runaway chain reaction in a bomb. Okay, if this gets stuck, it doesn't matter when you turn the emitter off, it's already kind of in a runaway. Okay, so the structure of the atom as we currently understand it is that there is a dense, positively charged nucleus that contains the neutrons and protons, and there's a large volume of space, okay, surrounding the nucleus in which the electrons can be found. Okay, so in fact, atoms are actually made up of a lot of empty space. Not as much as Rutherford thought, okay, but still quite a bit. Okay? Which is odd when you think, oh, well, but this is a solid object. If it's made of mostly empty space, why can't I just like pass my hand through solid objects? Well, remember, a lot of empty space is a relative term to the size of an atom. Okay? In solids, atoms are pretty tightly packed. And remember, your finger is, millions or billions of atoms thick. Right? You're not going to just push the atoms out of the way and pass your hand through a solid object. Okay, questions on that? That's good there. Okay. Okay. So this has to do with the second point of Dalton's theory, that atoms of the same element are identical and atoms of different elements are different. Okay. So atoms are made of protons, neutrons, and electrons. How can atoms of one element differ from another? Okay. Well, the properties of any atom or any element are based on the number of protons in the atom. I think I mentioned that yesterday, but I'm just reviewing it. Okay? So iron has 26 protons. Okay? Having 26 protons makes you metallic. Okay? Can give you some ferromagnetic properties. Okay? That is the ability to be attracted to a magnet. Okay? Things like that. All right? Having only, let's say, if we're talking about carbon and only having 6 protons, that makes you essentially kind of a black, non-metallic material that under heat and pressure can crystallize and become diamonds and things like that. Okay, so the number of atoms, or the number of protons in an atom determines the properties of that element. Okay. Now, in a nuclear reaction, after fission has occurred, okay, we often have different materials after because we've split these atoms. Okay, and one of the toxic byproducts is lead. So uranium, which has an atomic number of 92, so it has 92 protons, actually gets split up so much that you actually get lead. It's a radioactive isotope of lead. So it has 82 protons, but it's got way more protons than normal, or sorry, way more neutrons than normal. So it's heavy lead, is what they call it, and it's a radioactive byproduct, okay, of nuclear fission. It's one of those things that you'd see in the glowing green barrels on The Simpsons that Homer works with. Okay, would be one of the materials in there. All right, so does that make sense? Okay, big thing to remember there. Okay, number of protons is essentially what gives the differing numbers of subatomic particles, and we should probably say, in particular, protons. Okay. Now what you can see in this diagram is something that we'll just briefly touch on, okay, in Science 10 AP, not in regular Science 10. Okay? And that has to do with what are called orbitals. Okay? Orbitals are areas where an electron can be found. Okay? It's part of de Broglie's electron cloud model. It's part of the reason why Bohr's model is not totally acceptable. Okay? The different orbitals, as you can see, have different shapes. Okay? This orbital here, kind of the big circle, that's kind of like the lowest energy orbital because it's the one that's closest to the nucleus. Okay? Whereas these orbitals here, kind of the pink, kind of weird shaped things, okay, they would be higher energy orbitals because you can see at sometimes when an electron is in that orbital, it's quite a ways away from the nucleus. Okay? So there's these areas where an electron can be found, and each one represents a different amount of energy that that electron can have. Okay? And oftentimes you can find more than one electron in each orbital. Okay, so I'm going to pass out this question sheet here, okay, and I want you guys to answer the questions, use complete sentences, things like that. This is what the quiz tomorrow will be on, okay, is this stuff here. We'll give you a little bit of time to get going on that, and then hopefully we can start naming compounds today. All right. Okay, so idea of the atom was first proposed by whom? By Democritus. Okay, it was rejected at the time because
people believe the four element.
Right, people believe the four element thing. It made more sense. It was more practical and it worked. Okay, and he had no proof that there were tiny indivisible particles. It's really easy to say, hey, everything's made up of this stuff you can't see and I can't prove exists. Yeah, people aren't going to buy that. Okay. All right, number 2. What elements did the Greeks believe all matter was made of? Well, we talked about that yesterday. Okay. It's earth, air, fire, and water. Okay, and why did they think that was logical? Because they could see it. Okay, and we used some examples yesterday. Things like molten lava was some parts earth and some parts fire. Okay, and steam was fire, water, and air. Okay, all of that kind of stuff. It all kind of made sense to them because they could. It was something tangible. All right, for number 3, during the Middle Ages, which group of people inadvertently did a bunch of work on chemistry? The alchemists. Okay, but their goal was, of course, to get rich by making cheap substances into gold or finding something that could make you live forever. Okay. All right, in 1700s, okay, who came up with the atomic theory? John Dalton. 4 points of the theory. Everything's made of tiny particles called atoms. Atoms of one element are the same. Atoms of different elements are different. Okay, in a chemical reaction, okay, atoms are separated, joined, and rearranged, and essentially, sorry, I skipped the third point. The third point, essentially, you can't change an atom. Okay, is essentially what it says. All right, so the 4 points there. Okay, for number 6, okay, sorry, looking at his theory now, what part of his theory was wrong? Right, they're not indivisible. We can divide them, but it doesn't happen like in nature. Okay, it's not a natural process or anything like that. And it doesn't happen in a chemical reaction. Okay, describe in your own words the models of the atom described here. Give a brief explanation as to why each has been rejected over the years. Okay, do you think our current model may change? Yeah, it may very well change. Okay, I mean, we discover stuff all the time about the structure of matter. Okay, so the models are solid sphere. Okay, made sense at the time because we didn't have any evidence as to what it actually looked like. Okay, the discovery of electrons led to plum pudding. The discovery of protons and neutrons led to other models that we didn't even talk about. Okay, the Rutherford experiment led to the nuclear model, or the Rutherford model. Okay, then the Bohr model explained the arrangement of electrons, and then the de Broglie model improved on that to account for their changes in energy. Okay, as our knowledge increased, we discovered the atom had smaller parts. Right, parts of the atom: protons, neutrons, electrons. Protons are positive, they're in the nucleus. Neutrons are neutral, they're in the nucleus. Electrons are negative, they surround the nucleus in the cloud. Okay, 1 cubic centimeter of lead is much heavier than 1 cubic centimeter of carbon, so I have same volume of these two materials. Why is one heavier than the other? Right, it has more protons, neutrons, electrons. Essentially, lead atoms are bigger. Okay, if I had the same number of lead atoms as I have carbon atoms, it's going to have more mass because there's more stuff there. Okay. All right, nuclear reactors use atoms with very large nuclei, like uranium, which has 237 particles in its nucleus, for fission. Why wouldn't they use smaller, less dangerous atoms? Right, if they're less dangerous, that means they don't have as much energy in them, so why would we use them? The other thing would be target size. Okay, hitting an atom that has 237 particles in its nucleus is like hitting a really, like, you could put a bullet through the broadside of a barn. Okay, but shooting at an atom of hydrogen is going to be considerably more difficult. Plus, you can't split it because there's only one thing there, and there's only one proton. So you want to use big atoms. They're easier to hit. They have more energy. Okay, number 10, atoms are indivisible. Okay, why was that statement believed for so long? Because nobody could do it. Simple. Okay, nobody could do it. Okay, why is this still somewhat true? Because you can't do it by a chemical reaction or a physical means. Okay, it's only capable of being done if you have specialized equipment. Okay, like a nuclear reactor, okay, or something like that. All right, number 11. From what you know of the structure of the atom, how do you think the atom stays intact? Why do the electrons not fly off? Right, they're attracted to the protons. And when you get into physics 30, they talk all about why the electrons actually never crash into the nucleus. Okay, it has to do with all this intraatomic forces and things like that. Because, I mean, if they're attracted to the protons, theoretically, they should just go and stick to the nucleus, but they don't. Okay, glow-in-the-dark thing, we talked about that. That's the photosynthesis, the electrons going up and down based on changes in energy. So I will post your quiz later on today. Okay, watch for it.